this is 11.4 tree diagrams and the counting principle. The first objective, we're going to see the use of the counting principle. This is going to be very, very handy later on when we do what is called or and problems. So and problems is when you multiply, or is when we're going to be adding. But right now we don't need to worry about that because we're going to be doing the base level, which is talking about the counting principle. So the counting principle says, if the first experiment can be done performing in m ways, and the second experiment can be done performing in n ways, then the two experiments can be performed in m times n ways. So basically, if I multiply these two together, I get the entire sample space. So that's important because that's what the counting principle gives you, is the counting space. So once again, counting principle tells you what your sample space is. And as we learn from probability, this is very important to know because that usually becomes the denominator when we talk about probability. Also, when we talk about what tree diagrams are, which is the next objective, it'll also tell you how many branches you're going to have. So let's go ahead and just see the counting principle in place. Let's say you and a friend decide to try out a new restaurant for lunch. The lunch special states that you can order one item from a list of items consisting of an entree, a dinner, and a dessert. So first of all, entree, and I'm going to call this E, there are 5 different options. We have biscuits and gravy, salad, soup of the day, onion rings, or fried pickles. All right, so I'm going to put a little note that the entrees, there's 5 options. For dinner, you have your choice of chicken and waffles, pot roast, or barbecued ribs. So there are 3 options for dinner, which I'm going to call D. And then finally for dessert, you get to pick one of those. And your choices are apple pie, New York cheesecake, or peach cobbler. So there are 3 options for your dessert. So let me make that a little D. So to figure out how many different items we have to choose from, you can use the counting principle. So the counting principle basically tells me how many different ways I can order. So what I'm going to do is I'm going to multiply the number of entrees that I have times how many dinners we have and how many desserts we have. So the entrees was 5, dinners are 3, and finally desserts are 3. So I get 15 times 3, which is 45. So there are 45 different ways that I can order from this particular menu. And once again, that is the counting principle. So all I did was multiply those numbers together. So that brings us to tree diagrams. If you've ever done prime factoring, it kind of looks like this, but on the side. So as a reminder, prime factoring is breaking down a number that is not prime into prime values. So 20 becomes 2 times 10, and 10 is 2 times 5. So if I prime factor 20, I look at the end of my branches, and I get those prime numbers, which is 2, 2, and 5. So what a tree diagram allows you to do, it's similar in terms of prime factoring, it allows you to see all possible outcomes of the sample space. So when we do the tree diagrams, the first thing you want to do is to use the counting principle to determine what the sample space is. So in this next example, it says a radio station is having a contest in which 2 tickets will be given away to see the Foo Fighters. The station has narrowed it down to 4 people: Christine, Mary, Joanne, and Donald. Use the counting principle to determine the sample space. Okay, so if they have 2 tickets, on the first ticket, we're going to have 4 possible people. One of those people is going to be chosen to get that free ticket. That means that there are 3 left to get the second ticket. So I just wanted to kind of show you that. So the counting principle says first ticket, we have 4 people available. If one of those 4 people wins the ticket, which they should, then there's going to be 3 people available for the second ticket. And the reason why it's not 4 again is because we have to take one of those people out of those original 4 because one of them has already won the ticket. So 4 times 3 is 12. So I know there are 12 different possibilities that the 4 people can be chosen. So in order to figure out what those 12 different possibilities are, I'm going to do a tree diagram. So just like I said, the first ticket, the possibilities are Christine, Mary, Joanne, and Donald. Okay, so the second ticket, if Christine gets picked, then it could be Christine and Mary, Christine and Joanne, or Christine and Donald. If Mary gets picked, it could be Mary then Christine, Mary then Joanne, and Mary and then Donald. If Joanne gets picked, it can be Christine, Mary, or Donald. And then finally, if Donald gets picked, it can be Donald, then Christine, Donald, then Mary, and then Donald, then Joanne. Notice in these, I don't have repetition. I don't have Christine and then Christine on the second ticket because it doesn't make sense. Once Christine has picked a ticket, she's out of the running for the second ticket. So if I list out all these choices, I get, and I'm just following along these lines here, I get Christine then Mary, Christine then Joanne, Christine then Donald. Now I'm going to go down to the next one. My next choice would be Mary then Christine, Mary then Joanne, and Mary then Donald. So once again, all I did was follow the lines on the tree diagram. So my next possibility would be Joanne then Christine, Joanne then Mary, and then Joanne then Donald. So once again, I just followed these lines across, and finally the ones with Donald are going to be Donald Christine, Donald Mary, Donald Joanne. So right here are my 12 different choices that I have, and I can count them really quick to make sure I have all of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So those are the different ways we could win the tickets. So the sample space is listed out. I just did that by doing Christine, Mary, Christine, Joanne, Christine, Donald, etc. For part C, it says, what's the probability that Joanne will not get selected to attend the concert? Okay, since I already did my tree diagram and wrote out all my possibilities, I can just rewrite these really quickly. And once I get done rewriting them, what I'm going to do is I'm going to highlight anything that does not have a J in it, because the question says, what's the probability that Joanne does not get selected to attend the concert? Okay, I know my sample space again is 12 because there's 12 different possibilities. So remember, for probability, it's the part we're interested in over the sample space. Okay, so once again, we're looking for Joanne not to get selected. So I'm going to highlight anything that does not have a J in it, because remember, I don't want the ones that have her selected. So when I do that, I highlighted these 6 possibilities. 1, 2, 3, 4, 5, 6. So the part I'm interested in is the 6 that does not select Joanne, and then the sample space is 12. So if I reduce that down, I get 1/2. So she has a half a chance of not being selected to attend the concert. Okay, so hopefully you guys get that. And that's actually, 11.4 is super quick. So once again, this will get you through your homework. Remember, with this particular example, that's without replacement, right? So we don't replace the person back into the pile to win another ticket. If it's with replacement, remember, your sample space doesn't change. So just as a reminder, that could happen with the tree diagrams. Okay, and good luck, and I'll see you guys on Monday.